So this video shows you how you can solve an 8.4 or an 8.5 extends problem. What we're looking at is taking a combination circuit, so something that has both series and parallel components, and looking to fill out a table like we've been doing with our individual series circuits or individual parallel circuits. So to start here, you'll see that I have a circuit on the left-hand side drawn. I have 4 different resistors, 1, 2, 3, and 4. They're all labeled for you. So my very first step here is I'm going to plug those numbers into my resistance column of my table. So for R1, we have 2 ohms. For R2, we have 3 ohms. R3 is 4 ohms. And R4 is 8 ohms. If you can think back to when we did combination circuits, what we're really trying to do is find an equivalent. So my very first step here is I took R2 and R3. These are in series. They come one right after the other, and I added them together to get 7 ohms. So I can transition from this first circuit here to the second circuit where I've simplified it a little bit. Now where you see R23, what that's saying to you is I've taken the resistance of resistor 2 and resistor 3 and added them together to get this 7. My next step here was to get these two, R23 and R4, to combine into one. To do that, what I did is I had to add them as they're in parallel. So I took 1 over 7 plus 1 over 8. When I get my answer, right, I remember that I flip my answer. I found that I used a common denominator of 56 here. So that gives me 856 plus 756. Together there, I get 1556. When I flip my fraction, I get 56/15. When I divide that out, I get 3.73 ohms. That's how I got this. Now in my last circuit here, I see that I have 2 ohms and 3.73 ohms. These are in series together. So what I have to do is take my 3.73 ohms and I add my 2 ohms to give me a total of 5.73 ohms. I'm going to put this into my resistance total. So 5.73 ohms. Okay, this is really similar to what you've done so far, nothing new yet. Now if I take a look at my circuits, my total voltage is 9 volts. I'm going to plug that in here over on my voltage. I get a total of 9 volts. Remember that when we use this table, we're really looking at using I is equal to V over R, or Ohm's law. So now, if I know my voltage total and I know my resistance total, I can find my current total, right? All I need to do is to current, I take 9 volts divided by 5.73 ohms, right? My voltage divided by my resistance to give me my current. When I do that, I get an answer of 1.57 amps. Okay, here's where things get changed up a little bit from what we've been doing so far. We need to remember some rules. If we are looking at something that's in series, it's going to have the same current. If we're looking at something that's in parallel, it has a consistent voltage, right? Remember, one path, one current. If every resistor has its own path to the battery, it gets to use the whole battery, and therefore you get a consistent voltage. So those are some rules that we need to think about as we progress through this. Our next step here, I'm going to change my pen so that you can see clearly where it is that we're working, is we need to figure out this first resistor. Let's start here. If I have a current that leaves my 9-volt battery, right? I've said that that current that's leaving my battery is 1.57 amps. Because this resistor is in series to my battery, I know that this 1.57 amps is also the current at my first resistor. So I'm going to take that number and I'm going to plug it in up here. Because remember, if there's one path or it's in series, you get the same current. Now that I've calculated this current, I can calculate voltage because it's my only box in that row missing. If I rearrange to solve for voltage, I'd multiply each side by R, and I get Ri equals V. So I can take 2 times my 1.57 to get my voltage. That comes out to me as 3.14. My next step here is I know that if this is my voltage, I'm going to write this above here. Oops. .14 volts. This much voltage is being used by the first resistor. So if I have a total of 9 volts and I subtract my 3.14 volts, I end up getting 5.86 volts remaining. This 5.86 volts remaining is what gets split between these two things, right? Now if we think back to things that are in parallel, because these two branches here are in parallel, things that are in parallel get to keep the same voltage, right? So that's saying that this branch has a voltage of 5.86 and this branch has a volt of 5.86. Now on the right hand side here, resistor 4 gets access to all of that. On the left hand side, resistors 2 and 3 end up having to split that voltage somehow. So we're going to come back to that one in a little bit, but we know that 5.86 volts is the total amount of voltage that's going to get used. Well, you start with 9 volts, so that 3.14 gets used by resistor 1 as the voltage continues to be powering the circuit, right? 5.86 is left to go down this branch and to go down this branch. So for R4, our total amount of voltage is 5.86. Okay, that allows us to solve for our current at spot 4, right? Because we know our resistance and we know our voltage, we can solve for current. So current at the 4th resistor, the amount of current that's running through that resistor is 0.733 amps. So now, on this side, 0.733 amps. I've figured out my current and my resistance for spot 4. I've figured out my current and my resistance for spot 1. All that's left is for me to figure out my current and my resistance at resistor 2 and at resistor 3. Okay? So, if we look back at our simplified circuit, okay, our next step is that we need to be able to solve how much current each of these are using. If we take the amount of current that we have as a total, 1.57 amps, I know that 0.733 of those amps is going to go through resistor 4. So of my 1.57 that reaches this point right here, right, 0.733 goes through resistor 4. The rest of that needs to go through resistors 2 and resistors 3. So 1.57 amps minus 0.733 gives me a difference of 0.87. Excuse me, that's a mistake there. It should be 0.837. So this amount of amps needs to flow through this branch of the circuit. If we look at resistors 2 and resistors 3, these are in series to each other. Remember, things that are in series keep the same current all the way through. So at both resistor 2 and 3, I can have a current of 0.837. I'm also going to fill those into my table here. 0.837, 0.837, and my unit is amps for both of those. I now have a resistance filled all the way down in my table and currents filled all the way down in my table. My last step here is to calculate my voltages. If I look back at the equation I rearranged earlier, voltage is equal to resistance times current. So I can take 3 times 0.837 to get my voltage drop at the second resistor. The answer I get there is 2.619. If I take 4 times 0.837, I get 3.492. Now my table is completely filled in, right? And let's talk a little bit about what all this means. So again, these resistances are the resistors' values, or the number of ohms, the resistance each of these carry. When we look at current, we need to look at the circuit and decide, are the items in series or are they in parallel? If things are in series, they keep a consistent current. Notice that for current 1, right, and the total current, those are in series to each other right in a row, meaning they get to use or have 1.57 amps of current run through it. That current then splits between two branches. Part of that current goes to resistor 4, part of that current goes to resistors 2 and 3. Resistors 2 and 3 have the same current because they're in series to each other. Resistors 2 and 3 split the current with resistor 4 because they are in parallel to each other. If we look over at voltage, you're going to look right away and say, oh, my voltages don't add up to my total. Remember that because in a combination circuit we have some series and some parallel parts, they're not always going to add up to that total. When you have all series, they should add up. When you have all parallel, you keep a consistent voltage. When we really get into what this voltage means, this is the amount of the battery that the circuit's using, right? So some parts of the circuit use more of the battery than other parts. As our current flows through our circuit, this battery is getting used. We start with 9 volts. The first resistor uses 3.14 volts of that. We then went to the bottom here and took 9 volts, and we subtracted 3.14 volts to get the amount of voltage left after going through the first resistor. That voltage then was equally split, right, or was the same for both branches of the parallel circuit. That's because parallel circuits have their own path to the battery. If we look at what that looks like here, your current could leave your 9-volt battery. As it flows down, it has two options. It can flow this way, or it can flow this way. Because it can't do both at the same time, you get that same total, 5.86, 5.86. These voltages that you've calculated in your table right here are voltage drops. That means how much of the battery is being used by each resistor. So the first resistor uses 3.14 volts of the battery. The second resistor uses 2.6 volts. The third resistor uses 3.49 volts. The fourth resistor uses 5.86 volts. Again, looking at how those don't add up to 9, you're going to get a consistent, or you're going to get something that adds up to 9 if you take one path. So the voltages for R, I'll do it in a different color here so you can see. If the current runs through R1, R2, R3, and back, you're going to get voltage drops that add up to 9 because the entire battery gets used in that path. That's what keeps a battery powering a circuit. If they take a different path, if it leaves and this time goes through resistor 4 and back, the voltage drops at resistor 1 and resistor 4 will add up to be 9, because no matter the path that the current takes, it needs to use the entire battery.